I'm going to perform compression analysis in DYNA. We're going to have our rod that will be compressed, and we'll see the simulation. This simulation for the compression will have two parts. The first part will be a pre-processing, then part two will be a post-processing where we can get results. Okay, therefore let's now begin the DYNA. I've already opened the pre-post for the DYNA, and if you want to change your geometry, you can go to just view. You can use fade. This is the default. Personally, I like using plain. You can reverse black white here using background color, reversing like that. For the toolbars, I like having an icon with a name. If you go to geometry view toolbar, I like using text and an icon. Others like icon without a text. You can see on this side. If you go to view toolbar, for the bottom toolbar, you can select icons. The name disappears, but I like showing both text and icon. Therefore, that's what I like using, name with an icon. The first step is to create a cylinder. I like using, you go to model here, you select model, that is another model, you select mesh because we need to use a shape measure. For the shape measure, we usually have, these are the types of entity that can be used, and I want to use a cylinder solid. Mine, I want us to use a solid cylinder. These are the parameters for the radius. I want to use 0.5 meters. Length, I want to use 5. Okay, these are the number of elements because it is going to mesh our cylinder, and it will have, let me use 24 number of elements. If you create, you can see what you form here. For the number of elements along the length, if you go front, let me just go top. If you increase you can see now you have 5. 1, 2, 3, 4, 5. If you change this one here, maybe to 40, reject, create. Now these elements are 40, all of them. These are the elements along the x-axis. These are the elements along z-axis. But I want my model to be along z-axis. If you go isometric, let me use isometric. You can see now my model is along x-axis, but I need to be z-axis. Therefore, you select 1 here and put a 0 here. Reject, create. Now my model is along z-axis. If you want maybe your model to be at an angle of 45 with the x-axis, just use 1 on x-axis. Reject, create. You can see my model is slanted, but now I need to be purely along the z-axis. Then you can select done. Okay, if you want to see the mesh, you can see the types of mesh we have. Our body is now completed. Then I want us to have, I want to have two parts, bottom plate and a top plate, because I want to fix top plate and I want to apply the force on, I want to fix bottom plate, apply the force on top plate. Therefore, because I want to use indirect load, okay? Then for me to do that, you go to the, I want to go to the element, let me see, I want to use, I want to use element generation. Here it is. In the mesh, use element generation here, yeah. And I want to generate elements using, I want to use I want to use a solid one. I want to generate a solid one here using a phase drag. I want to use a phase drag option. I want the element thickness to be 0.1 with one segment. I'm going to illustrate what this means. What I mean is I'm going to use this existing solid and I want to pull another circular solid on top of this is a different part. The reason I have a part ID, different part ID, and do the same on the bottom section. Therefore, for the direction, I want to use along z-axis. I'm using a 1. And I want to use a solid face drag. Now you have to pick the face of an element. Let me zoom in here. If you select now one element, I want all the elements on the top face to be selected. Therefore, you activate propagate, then you select this element. You can see now after selecting the propagate, you just select one element and all the elements on this face are selected on a solid face. Then these elements, we're going to drag them along the axis by this amount. Let's see what happens. If you now, let me see from front view, let me zoom out. You can see now we are selecting the top element, the top face for the solid face, and we want to drag them to create another part ID from the top face. Therefore, this part and this part becomes fixed. It will be fixed along this face. If you change the elements, see what happens. Two elements are formed. Select three elements are formed. You can see 1, 2, 3. I wanna use 1. If you change thickness here, becomes longer. You can see now the thickness changes. And I wanna use just a thickness of 0.1 with one segment. Then you can accept. You have now a part ID. I want to zoom out because I want now to select the bottom face and create another plate on the bottom side. Again, if you don't select propagate, if you select, I want to use now a new part ID, still a solid by solid face drag. Remember, not offset drag. Remember, I'm using mesh, element and mesh, element generation. Then I'm using solid option for the solid face drag. I want to select this face and drag that face. But now I'll use negative z axis, put a negative, and you select the element. See what happens if you don't select propagate, it will select only, you have to select one by one. But you can use propagate to save time because it will select for you automatically. Then you can create, then part ID 3, then say done. You can zoom out. You can use isometric. You can see now our finite element method parts are 3. We have a cylinder. This one I can always name the cylinder. We have our top plate element number 2. Always right click, add the name, call it top plate. Top. This is a top plate that is movable like that. And we have a bottom plate that is fixed. Just right click. This one is a bottom plate which is fixed. It is good to name your parts in form of descriptive so that you don't get confused. That is about that one is about elements uh, parts creation. Okay, let's go to the step 2. That is now we define load and we define, let's now define load. Because we're going to put load on this plate. I'm going to press to put load on this top plate. It will compress my cylinder, and from there our cylinder will start to deform. You can go to FEM. I want to use a keyword manager. For the elements, for the mesh element generation and shape measure, you can still use the first one, element mesh, shape measure, to create your cylinder solid, and element generation to create two, two parts that share the same contacting surface with our cylinder. Therefore, you go to firm model add keyword manager. Okay, take some time. I want to first of all to define load. Therefore, I will go to all. I need to now select load. For the load, I want to use a rigid body. I want this body to be rigid. Therefore, I'll use a rigid load. This a rigid body because this body will be rigid. This body will be, our cylinder will be elastic, and our bottom plate is like a floor that is rigid. I'm going to assume that our floor is bottom plate that is rigid, and our top plate that is compressing the cylinder is still rigid. Therefore, select a rigid body. Okay. For the part ID, I'm going to use top plate. Okay, done. This is a load rigid body that will be applied on the top plate. Okay, for the DOF, remember now this body will always move along the axis. I want to use along this. I want to go along the direction. Therefore, for the DOF, degree of freedom, I want to use 3. Therefore, select 3. Why am I using 3? Because the load will be acted along the axis. You can see the direction of load action. I'm using 3. What about we need a load. You have to define the curve that defines the load. We don't have this load. I will define it later. Therefore, let me first of all accept and select done. Let's go back and define the load. I want to define curve. I want to define curve. This curve, I want to give this curve as maybe load versus time. Okay, load ID is the one. I want I want to use the, let me, I was saying I want to use this one is a load ID. That will be, you can see load curve identifier will be 1. Then for this one I want to use 0 as my default because I want to use load curve used in transient analysis only, or for other applications, because my model will be a transient, because a transient analysis is analysis that varies with time. I want to use 0 here for the transient analysis. For the SF, I want to leave this one as default for now. Then you put data here. Here is it is the time. A is the time. B is the load. I want to use 0, 0, insert. Then I want to use, after 1 second, my load will be 10. Insert. If you plot, this load curve, let's see what happens when you plot. I'm not sure why doesn't want to plot. Okay, accept plot. You have to accept first. Yeah. can see now my after on 00 our value is 0, but on 1 second here, this is the time on x-axis, the load is 10. Okay, then can done. If you go back to the can collapse all, then go back to the load. On the load here, I want to use a rigid body. Then for the load curve ID, select the load versus time. If you read, you can plot. Yeah, can just verify by reading and plotting. Therefore, you can now say done, done here. Now my load for the rigid body for the part ID number 2, and I'm using number 3 because the X direction is the load action, and I'm using 1 because I only have one load curve ID. Then this one is the scale. I want to scale. Remember for the load here, for the let me go back and read. I'm using a value of 10. If you plot this, consider the value of 10. I want to scale this. Let me scale. You scale using an SF. I want to scale this value maybe to a 10, maybe 10 million. Let me assume it is a 10 million newtons. Therefore, I want to use a negative 10 million. Why am I using a negative? Because the load I defined my curve defined on the positive axis on z positive, but our load will be acting on a negative z axis. Therefore, you put a negative to scale. You can see SFA is the scale factor. It will take this value of negative 10 million, multiply by the value of our curve here, multiply by this value of our load versus time curve, then it will get the final results here. Okay, but now note, don't use this. Leave this one as a default for now. Done. Ignore. I want to scale this instead. Therefore, put a negative 10 like that. Accept. Done. You either scale on here, load curve scale factor, or you scale on the curve itself. If you go back to, let me collapse here. If you go to the define, let me go back to define, you go back to curve, you either scale here, or if you want to scale here, you can still scale here, but I prefer you scale on the you scale when using the actual load. I hope that is understood. Yeah. Then the next thing is I want to define the material. You have defined, so far you have defined the curve, can see define. You have defined curve, you have defined load, but now we need to define the material for this. Therefore, you go back to all and you select collapse all, you select mat, look for mat. MAT for material. It is, I want to use first material as elastic, to number 1, new ID, call this one as mine. I want to use a steel. This is the material identification. This is the mass density. This is the Young's modulus, that's 200. Position ratio 0.3. Can say now accept, done. That's first material. Then I need to define rigid material, rigid plate for the rigid plates. Therefore, you can go to material number 20, new ID, call it rigid plate material, the same density, same Young's modulus, same position ratio, accept, done. That's how you define material. Next, we need to define section. You go back to the all select section. Yeah, and these three are solid. Therefore, we define solid here. Define solid, new ID, call them solid, add. For the section, I want to use a constant stress solid elements. Does that the stress is constant solid elements type of element form, that is one here. You can do more research on the sections here. Okay, therefore you can say accept done. I can go back to part. I want to go back to part to assign. For the cylinder, you need to assign section, that is a solid, done. For the material, it will be steel, done, accept. Okay. For the plate that is movable, let me go back to the material first. It's something I want to illustrate. I want to go back to rigid. I want to still, this is a rigid plate that is movable. Let me just have each material that's a movable. New ID. This one is fixed. Accept. Okay, I have a rigid material. One is a movable. There's some parameters I want to illustrate here. That is con 1 and con 2. This con means constraints 1 and constraint 2. My plate is movable along the axis. Therefore, for the constraint, do not constrain along the axis. Therefore, constrain only on x and y displacement. Therefore, I'm going to use 4. This means that the movable material is constrained only along x and y axis, but it is free to move along the z axis. But rotations, I want to use 7 to constrain all the rotations. Do not rotate like that. Accept. Go to the rigid. The same case, do not rotate. Also, the rigid one doesn't move either on X, Y, or Z. Therefore, I'm going to use 7. Accept. Done. Therefore, if you go back to part here, that was very important step. The leader is going to use section solid. And okay, for the material, still done. Top plate, you have to accept. Go to top plate, that is movable. For the section, is still a solid, done. But for the material is a movable, that is a rigid plate, done, accept. Go to the, leave this one as the default. Go to the bottom plate, section is a solid, done. For the material is fixed, done, accept, and done. You have defined our part, and you have defined the section and the material for the parts, because you have 3 parts on this model. That is a cylinder, you can see the cylinder material is steel. The top plate that is movable is have also defined a rigid plate that is movable, and vice versa. Okay, next step is now to define simulation control. Okay, let's now go to simulation control here. Collapse. I need first for to select control. You go to control here. Termination. If you select control, always use termination to define the time. Termination. This means the end time is 1 second simulation. Without this, you can see here termination cycle, normal cycle. After 1 second, stop. Accept, done. That is about the control termination. There are 3 parameters that are very important in order to define under control. The first parameter is implicit general. You have to define the implicit general because By default, the ls DYNA is for the explicit dynamics. Explicit dynamics, but now ours is not a dynamic, it's a static case. Therefore, I want to use implicit. Implicit is the best solver for the static analysis, but for the dynamic analysis, it's the best to use explicit. And you know the difference between the dynamic analysis and static analysis. For the static analysis, all the forces generated in your system, maybe you have a force along z-axis, along y-axis, along blah blah blah. The summation of those forces must be zero for the static analysis. But for the dynamic analysis, due to the inertial effect, the body is always in motion using a Newton's second law, that is, the summation of forces in your system equals mass times acceleration. In this case, we're going to use static analysis, and we need now to define that in implicit general. Therefore, look for the implicit general here. You can see here for the flag, I want to switch. By default, it is 0. You can see it is 0 because it assumes that our system is explicit, but ours is implicit. This is how you switch from implicit to explicit. I'm going to use 1 here for the implicit general. This will tell my software that I'm working with an implicit analysis with a time step of 0.01 or 0.02 to save time to run. This one means it will have 50 steps because you have to take 1 divided by the divided by 0.02 and this one gets 50. Accept, done. That is first implicit general, whereby you assign either analysis to be explicit or analysis to be implicit. Next, I said there are two types of analysis. We have a static analysis and we have dynamic analysis. How do you tell your system that? How do you tell the software to conduct either static or dynamic? You use implicit dynamics. You select now implicit dynamics. On the implicit dynamics, I want to tell the software that it is a static, that is 0 here. I have to make sure that this one is a 0. You are telling the software that our analysis is static. If it was dynamic, I could have selected either 1 that uses a Newmark time integration or 2 that uses a model superposition. But now I'm using a dynamic static analysis. Accept, done. Lastly, for the implicit analysis, remember in the termination here, we used 0.02. I used the 0.1 second as my I used 1 second as my edit time. Sorry. I used 1 second as my edit time. And if you go back to the implicit general, I used a 0.02. In fact, let me use a 0.01 to be a little bit more precise. This is my time step. I want to tell the software that this time step should not be constant. It can change this time step depending on the nature of analysis. Okay? How do you do that? You use what we call implicit auto. Go to the implicit auto. For the implicit auto, I want to use automatically, can see, we can either have constant time step, that is 0.01 constant, or it can always adjust. I want to use adjust it implicit. I want to use 1. You can automatically adjust the analysis for the time step. Accept, done. If you go to model, you should have in control, you have defined auto, dynamics, general, and termination. That was very important step. Okay. Next, we need now to define database output. You go back to model, collapse all, because we need now to get output from our analysis. You go to the database. I want to use a binary 3D plot. Therefore, the result will be, we are going to get results here. It is going to plot. For this one, for the DT, I want to use 0.01. This means this is the time interval between output. After 0.01, I need an output. After another 0.01, I need an output. Okay, just that. Accept, done. Model. We have defined control, database, we have defined the curve, we have defined load, we have defined material, that is elastic and rigid. Let me go back to rigid. In the rigid, we have two materials. You can see we are done. That is done. And we have also defined the section that was solid. And we have assigned mat and section to the part because you have three parts here. That's fine. Therefore, next step is to save the analysis and run the simulation. Therefore, let me do that. Okay, I have already saved my model. Next step is to run your analysis. You go to file, you select run ls DYNA. You go to the input, you just select your file where you saved your file. Here it is. Open it. Then from there, this one I can delete. This one was my previous job. Then you can run. It will run your your analysis. You can see now running. It can see the status percentage. Yeah. Therefore, in my next video, I'm going now to illustrate to post-process the results after running. We're going to post-process the results here. See you in my next video.